The next speaker, Mr. Naib.
Hello. Hello everyone. Myself Samira. I'm a PhD researcher at Kent University in Belgium, and I will be presenting a work which is a part of the project where we determine structural integrity of weldings and improve the current structures including heterogeneous patterns in the welded structures. In this presentation, I will be deriving some analytical equations of limit load predictions of a weld, lower bound and upper bound, and then I validate it with numerical simulations. To start with, the overall picture of this presentation would be the integrity assessment of a welding. So if we consider a pipe, and part of a pipe will be a weld, and if we see the weld, we have different zones in the weld, that is heat affected zone, base material of course, and weld material. And these weld material are characterized in standards and also in many procedures as they have material heterogeneity. That means the strength properties, and it will be varying inside the weld region, and also the presence of defects or flaws. The flaws cannot be avoided in a weld as there will be different reasons like inclusions or porosities and so on. And these flaws are rejected by workmanship standards and are classified as defects. And these defects can be or cannot be, depending on the situation, be dangerous to the weld. So the engineering critical assessment is one of the major procedures where the integrity assessment is performed. And to perform this engineering critical assessment, we need stresses around the notch or around the defect. We need the location of where the defect is present. They are characterized using ultrasounds or many other techniques, and the properties of the material. And with this, we can do the engineering critical assessment and assess the integrity or the life of the weld. And if we see the weld, we have the root, which is normally a smaller region or a less thick region, and we have a cap, and the defect can be an example of a defect present in a weld, which was given in the TWI website. And ECA techniques normally they don't consider the aspects of strength variations inside the weld, because when there is a repair welding or a different type of welding, there will be the variations of strength, which can be seen like this. There is a defect, there is a variation of material properties varying from very low hardness to very high hardness, up to 50%. And this, the ECA simplifies and consider it as one material, and in the weld. We leave the heat affected zone now, but we just consider the weld. And this can be dangerous because if the defect present in the root region or a cap region behaves entirely different under loading conditions. And this has to be considered, and this is the idea of our research. And to predict the integrity of the weld, we consider limit analysis. The limit analysis is basically the estimation of critical load when the plastic flow is unconstrained. That means the load does not increase anymore up to a certain point, and when the deformation is increased. And this is one of the estimation of integrity, and this is done based on several assumptions of course. And in this plot we can see there is a displacement and load, and there is no strain hardening. The strain hardening effect is neglected, and also the material is a 2D plane strain model or a plane strain material, and this is considered, and it is a simplified model basically removing all the heterogeneity and aspects of the weld. And this is chosen so that we can predict the weld based on the load criteria. So in this work, I will start with the analytical limit load predictions. That means we have a lower bound approach and we have an upper bound approach. Lower bound approach means when there is a structure, a welded structure which is performing, which is under loading conditions, we say that if it fails up to 50 years, we say it fails at 40 years and we want to replace it. So that means the structures will mostly be safe. And we have an upper bound approach, and which is normally we say if the structure can work up to 50 years, It may go up to 60 or 55 or 54 years, something like that. I will explain why we consider that theory, because it doesn't make sense initially. And then I will use the numerical model, which is a heterogeneous SENT, that is single edge notch tension specimen, to validate the numerical model. And then I will also explain the finite element model which I use. And then I compare the analytical model with the numerical model, and I'll see what are the differences we observe in this research. To begin with analytical limit load predictions, I start with the lower bound approach. So basically the lower bound approach is the conservative approach, which most of the industries prefer, because the margin of error is comparatively lower than the upper bound approach. So the structures are normally safer if we use this approach. And I use this equation of P is equal to sigma and area, that is normally stress is ratio of force and area. So that equation is normally used, and we have the forces inside the single edge knot tension specimen, which is clamped at one end, the displacement is applied at the other end. This equation does not consider the heterogeneous aspects inside the weld, and that is the aim of this work, to improvise it. So we consider a two-region weld, which is having a lesser, the lower strength region in the root, or the higher strength region in the cap, or vice versa. We try those things, and I update the equation based on mismatch ratio. Mismatch ratio is the ratio of yield strength of a base material, weld material to the base material. This was the ratio which was used in our university by my professor, which was published in the research paper recently. It gives a better idea for assessing a weld. Using that mismatch equation, I improvise the equation using two different criteria for the mismatch. And one criteria is based on overall global approach, where we have one weld material. Because in this case, if we consider the whole region, in this case, it does not make sense, because the slip lines or the deformation lines, it avoids the cap region. And if the cap is very hard or soft, this equation gives a different value. So that equation will be improvised, or we take the minimum value of the other equation, where this is rearranged and this form is obtained. So basically we are trying different approaches to obtain the minimum value of that weld. And the next one would be the upper bound approach, where we get a limit load which is higher than the actual limit load, but it is not too high, because this estimation will give us the exact or the actual limit load of the structure. It helps actually. And for that we use this equation, where there is a notch, and when there is a deformed displacement, the band theoretically goes at 45 degrees, and we take the average of strength properties along that line and integrate with this equation. These are the two approaches which are analytically used in this, and I will go towards the numerical model to validate this equation. We have a numerical model, and I take these 4 cases where the different distances of cap and root and the notch distances are different, also 3, and we give different mismatch ratios of the weld, that is the strength of the weld are different, and then I model it in the finite element abacus model. And we have the model like this, which has a notch depth A, which is converted from A by W. The W is used, it is 15 mm, the length of the specimen is 200 mm, and we use this model. And J2 type plasticity is a 2D model with plane strain conditions. And we have a notch with the radius of R, that is 0.005 mm, and this is the weld with 2 different materials. To go with the results, we use the limit bound of lower bound and upper bound approaches, and we do the simulations and plot it over the analytical and finite element graph. Basically here we have an overestimation region and an underestimation region. And if we see here, the lower bound approaches are basically underestimating, showing, but it's not very conservative. So that can be seen in this equation. So basically we can say this equation is valid for our approach. And then upper bound, if we see, it is almost equal in the one-on-one line, and some equations are above. That is, it's overestimating the equation, which is also successful in this work. That is the plan. So when we see the observation, the overall estimations are 15%, the differences between the analytical and numerical equations. And then in the lower bound, the average difference is 6%. And 6% based on other equations, it is not very high. So we can say that this is an improvised form of the equation available from the currently available to the other equations. And then we see the upper bound equations where we see certain overestimations or certain underestimations. Overestimations, why we think it's because of the avoidance of the slip line going straight. And in our previous work, we have seen that the slip lines does not go straight, where it avoids the hard region and makes a different angle. So that could be one of the reasons. And the second reason would be the strain. This equation was based on strain hardening, and we do not consider strain hardening in this equation. So with this, the numerical and analytical limit loads of the upper bound is 5% difference. So basically, the lower bound and upper bound, we have around 5 to 6% difference. And with this equation, we plan to improvise with using different forms of the weld, more complex forms with different notch depths, and obtain a good idea of how the equation works with different cases of the weld. And basically, in this presentation, we saw the lower bound approach which we developed in this work, and the validation using the numerical model, and then we saw variations up to 5%. Which is acceptable in our idea. I would thank you guys for listening.